neutrons. One way to accomplish this is with a small linear particle accelerator. We start out with two types of atoms. One type of atom contains a nucleus consisting of one proton and one neutron. We call this type of atom deuterium. The other type of atom contains a nucleus consisting of one proton and two neutrons. We call this type of atom tritium. Suppose we accelerate the deuterium towards the tritium. This can result in a collision which produces a helium nucleus and a neutron. In order to accelerate the deuterium to the high speed that's required, we need to apply an extremely strong electric field. Creating this strong electric field requires creating an extremely high voltage, and this can be accomplished with a high-voltage ladder circuit. Although the electric field will exert a force on the positively charged proton inside the deuterium, this electric field will also exert a force of equal strength in the opposite direction on the deuterium's negatively charged electron. Therefore, the total net force will be zero, and the deuterium atom will not accelerate. In order to overcome this problem, we need to get rid of the electron. We can do this by having another electron collide against it. Once the electron is gone, the deuterium atom will have a positive charge, and it will be possible for the electric field to cause it to accelerate. The deuterium is stored in a material which we will call the filament. If current passes through the filament will heat up, causing deuterium atoms to exit. We have another material, which we will call the cathode. If current passes through the cathode will heat up, causing electrons to exit the cathode. If we then apply an electric field to these electrons, they will collide with the deuterium atoms, knocking the deuterium atoms' electrons out of their orbits. If we then apply another much stronger electric field, the positively charged deuterium atoms will accelerate towards the target, which contains lots of tritium atoms. This will create neutrons traveling away from the target in all directions at extremely high speeds. If we leave this device on, it will produce a continuous supply of neutrons. We can control the rate at which neutrons are produced by adjusting the current passing through the filament. If we increase this current, the filament heats up more, deuterium atoms are released at a faster rate, and neutrons are produced at a faster rate. The filament current and the cathode current are just for creating heat, and these currents are not related to the electric fields discussed here. If we want to abruptly turn the generation of neutrons off altogether, we can accomplish this just by turning off the electric field that accelerates the electrons from the cathode into the deuterium atoms. If we turn this electric field back on again, the generation of neutrons will quickly resume. Much more information is available in the video titled Nuclear Physics, and please subscribe for notifications when new videos are ready.